I guess we can probably go ahead and get started. So yeah, today we're going to be continuing to hear from Stephen Duan, lead developer at zkM. He's going to be doing, I think, some demo for us today and talking a little bit about programming. So Stephen, go ahead and take it away.
Okay, thank you. Okay, thanks everybody. So today I'm going to introduce the zkMIPS. Yes, I think yesterday I have a brief introduction about the zkVM, and I also introduced what kind of tech stack and what kind of components we need to build a zkVM. So today I will go through how we build a zkMIPS, and I think I hope we can have more understanding about zkMIPS, and meanwhile we can hands-on the zkVM and to get a more concrete concept about what a zkVM and how to use the zkVM. So so before so basically we as I okay, maybe I can have a brief summary about yesterday talk. Let me share the documents again, because when we begin to discuss about the MIPS, I think we need to get a more detail about why we build a zkMIPS. So okay, let me share screen. Okay. Okay, so basically we know there are a lot of zkVMs right now, like the RISC-0, like the SP1 or StarkNet or zkWasm, Madden. Yeah, so basically there are a few different instruction set architecture like the MIPS. We are the only one that implements a MIPS-based zkVM. Basically, all one labs declared that they claim that they are building a zkMIPS, but we don't see the code. So I think zkMIPS are the first one that implements MIPS-based zkVM. And for the RISC-V, yeah, there are a lot of zkVMs that implements the RISC-V, like the apart from the RISC-0 and SP1, the pod labs, the pod labs, and the also this like the yeah, that the Lita Valinda, they also are going to are trying to support the yeah, I think like the pod labs, they are also support the RISC-V. Yeah, so and for Watson, it's kind of instruction set that I say that's used most in the web applications, because it's very efficient to manage the memory, and it's safe to limit the memory usage. Okay, so so I think the best the biggest difference between the RISC-V and MIPS is that MIPS is more yes, we say it's more web. We say it's stable, it's comprehensive, and it's more established, because it's more mature than the other instruction set, like the RISC-V. Okay, so about RISC-V seems it's more young, and then, more and more people trying to build things on that. So it seems that RISC-V and the most important factor is that the RISC-V is totally open source. Everybody can extend the instruction set, the RISC-V. So I think that's another very important part when we take the ISA into consideration when we build a zkVM. Okay, so basically we are trying to take care of more and more existing applications that they want to use the zk technology in their products. Okay, so before we discuss we need to discuss why we build a zkVM. Basically, for most of the case, zkEVM or zk sockets is are enough. We already have a lot of zkEVM projects like the zkSync Polygon zkVM or the Scroll. So but that's not enough because we EVM because zkEVM bring a lot of scalability and privacy to the EVM to EVM compatible blockchain. But consider the other blockchain layer ones like the Bitcoin, like the Tone, like the Cardano, okay, like the Near. So for those kind of blockchains, actually there are no the layer 2 concept is not very it not become so important for them right now. Of course, they have the issue of scalability, but they don't really have a good solution. It's not like the EVM, it's not like the Ethereum. Okay, so that's why we need a zk VM. That means we cannot only run the EVM on the zkVM. We can also run them the move VM or the near VM or the avalanche VM on the zkVM. So that's we can use one VM for all. Okay, so that's why we need to build a zkVM. Another very important is if we want to push the zkP into mass adoption in the markets. Cryptography is Web3 markets is one side, and we also have a lot of scenario like the zk identity, like the zk machine learning, like the zk maybe the zk TLS, transport security, transport layer security. Okay, so we actually have a lot of scenarios that we need to prove that the third party, the untrusted party, has run our code without any malicious behaviors. Okay, so that's basically why we need a zkVM. So okay, so for the zkMIPS, actually the zkM starts from the hybrid rollup. Okay, it starts from the hybrid rollup because as all we know, it take more about because the MIPS project is an optimistic layer 2, and it's usually takes 7 days to reach the finality of the layer 2 transaction on the layer 1. So that means if we want to withdraw some asset from the layer 2 to layer 1, so we need to wait 7 days. But if we combine the zk proof and the optimistic rollup, is maybe reduce the finality time to less than 1 hour. Less than 1 hour. Oh, sorry for the typo. Okay, so that's the first use case of the zkMIPS. The second one is we are building a Gov network. Gov network is a Bitcoin there too. And Bitcoin is a very powerful layer 1. And but this is it cannot support the Solidity-like Turing complete smart contracts. The Bitcoin provide us the scripts, but it's really hard to use the script to do some to build something. And like for example, if we want to build a layer 2, we at least we need the layer 1 to can run a zk file. But if we want to implement a zk file, zkP file or the by the Bitcoin scripts, it's very difficult. But the truth, but the good news is that we have the BitVM2 right now. And BitVM2 can can support. It's very perfect. I mean, protocol that can offload the can verify any computation of chain by Bitcoin scripts. So that means we can use the BitVM2 to verify the to run the zkM's zkM's verifier, and then we can realize the real layer 2 for the Bitcoin. Okay, so the end game, I think we think is the integral app. Yeah, also for the integral app, maybe we can take a look at its white paper. Basically, it's one to connect all the layer ones, and as we know, we have a lot of layer 2s, and so different layer 2s like the different group, but it's hard to communicate between the different layer 2s. We need to bridge back to layer 1 and then go to the link the other layer 2. So it's actually it's very it's a bad experience, I think. So why can't we communicate between different layer 2 directly? So that's maybe the next step for all the zk projects or the zkEVM projects they want to tag down. Okay, so basically that's the so I don't give any example about the zkML or zk identity or zk TLS or zk Oracle, because it's really easy to to move or to migrate the application specific zk application to the zkVM based application. Okay, so I think except that the developers can use the high level language, the formula, which are formula for most of the developers to implement the socket or the verifiable program. Another point is if we use the zkVM, we actually don't have to audit the socket, because you just need to audit your program, but you don't have to care about the sockets, because the zkVM can guarantee the correctness, the secondness, or the zk and the soundness, completeness of the zkP. Yeah. So basically that's the benefits that we use the zkVM. So basically for zkVM, as for general zkVM, we have different components. Like basically we have the inputs and outputs, input and outputs units, and we also have the programs. We also have the memory, emulator, and the hash or the other units. So okay, so here one things we need to take notes is different from the sockets, there's application specific sockets. We actually the one of the inputs is a program, but for the application specific circuits, the program actually we just write the sockets for the program, right? But for zkVM, we write the sockets for the VM. Okay, that's the difference. So okay, so that's the basic architecture of the of a VM. But for zkVM, actually, we still have the VM because we need the emulator. We need to simulate all the instructions. We need to run the programs to generate the different segments and emulates the state transition. But we have another very important part is the prover and the witness generator and the input commitments. That means we also provide the inputs, and meanwhile we may need to input the commitments of we need to calculate commitment of the inputs. Then we can use the commitments as the public and the outputs commitments as the public input of the sockets. And then we also generate the proof. Okay, so basically that's the zkVM. So when we consider, designing the zkMIPS, yes, basically I have a brief introduction about what we need to take into consideration, like the architecture. We have volume architecture. We have the Harvard architecture. Basically, most of the zkVMs choose the Harvard machine, and so we have 32 general purpose registers and 4 specific registers, and it's basically it's a module design. We have different components and different trace table, and different engineer focus on different components. Okay, and we have a channel or the bus between the different components, and use the lookup or the lookup scheme to guarantees the identity of the shared value between the different tables. So here we use the arithmetization. We will use the air for the VM part, for the VM's arithmetization, but we use the plankage for the recursion and the recursion. So that means when we do the proof recursion, actually we approve the aggregates computation. So naturally, because zkM is built on the Planck tree, so basically the Planck tree provide the proof aggregation and the recursion. So we can benefit a lot from the Planck tree actually. And okay, so the native field is got locks. Okay, so this is a very important factors we need to take into consideration, because different fields can bring different proof efficiency, proof size. For example, take the risk zero as an example. They use the baby bear, so you can see that, and the SP1 also use the baby bear or the M31. So those kind of like the baby bear or M31, they are actually or the elements of their fields just takes about 31 or 32 bits, but for logs it takes about 64 bits. So eventually the proof size is different, and the proof time is quite different. Okay. So basically, for zkMIPS, yeah, I have a brief introduction yesterday about this big diagram. I think I will take examples after then. I will not go to more detail here. So when we have the first step is we generate the trace. We use the executor to run. We use the emulator to run the binary and generates the trace, and then we make sure that all the trace can satisfy the constraints, and then we will generate the witness polynomial the constants polynomial, and they use the PCS, the polynomial commandment, to generate the stack proof and public inputs. And then we use the proof recursion and aggregation to generate the stack proof. So eventually the proof size on chain is very, very small. So because we use the group 16, so the final proof, the final size of our stack proof is about 200 bytes. Okay, 200 bytes. And of course, we have a verifier on chain, and we have the approving network here. So that means different segments can be proved in parallel. Okay. Okay, so this is okay. So that's the basically that's we have for each segment we have a program counter and its memory and the memory space, and then we different modules will different instruction sets will be executed, and then we get the next program counter, the first memory space, and we generate the execution trace. So okay, so I think so that's the example. That's a very simple example that we mimic the execution process. For example, yeah. So basically, when we run the perform the instructions, actually we are filling in this trace table. So each register is being to represents the state. Okay, like the real register R4, R5, and R6. Actually, it can be mapped to the column name in the trace table, and we also have a lot of intermediate register, because we need to limits the degree of the polynomial. So basically, the biggest degree of zkMIPS is 3. So that means we cannot. So all the expressions, all the constraints expressions in zkMIPS is less or equals to 3 in zkMIPS. Okay, so basically when we have this trace table, we begin to, we have to calculate two types of polynomials. The first is the constraint polynomial. Okay, so for each, for different constraint instruction, we have different constraint polynomial, right? Okay, and finally, we will, combine all the polynomial by the linear combination, and to get a composite polynomial. And then we use the composite polynomial to calculate to calculate its quotient polynomial. Meanwhile, we also have the trace polynomial, like the R0, R1, R2, and R6. Okay, so then we use the PCS to commit the quotient polynomial and the trace polynomial. Of course, this is just from for the single table. If we have the lookup table, basically we need to commit the lookup table. Use the PCS. Okay, so as I explained, we can generally speaking, we can. It's not efficient to use a single table to represent to the emulate all the instructions, because there are a lot of zeros. For example, if all the instructions is the add, but we have another bunch of columns that are for the logic maybe for the logic operations. So all the logic operations, so all the cells of those columns would be 0. Okay, so that means the table would be very sparse. Okay, so we basically split the big table into different small tables, and then we commit on each smaller table. But in zkMIPS, we actually have we have 6 sub modules or sub tables, sub trace table, and we commit each trace table, and then we use proof aggregation to generate final root proof. Okay. Okay, so that's basically how we how lookup works. Because for the arithmetic, basically each each instruction should be handled by the CPU. So we can have one CPU trace for each instructions. And meanwhile, for the memory, also the of course so when we generate the lookup table, we need to make sure that the arithmetic table can be looked up in the CPU trace. But sorry that the memory is not very correct, because almost all the components handle communicates with the memory, so there should be the line there should be some lines between the arithmetic and logic between the and the memory table. Okay, sorry for that. I will change it. And meanwhile, we use the cross table lookup. We use the lookup. Okay, so lookup is really efficient because it's basically the proving complexity is related to the smaller table. I say the smaller table because it's just related to the table that's being looked up, not the full table T. Just it's related to the table F, not the T. Okay. So okay, so when we have all those kind of components, we basically we have the continuation. Yeah, for the continuation, I think it's really easy to understand that we just emulate the binary. We just perform simulates the we just simulate the binary, or we just perform every instruction of the binary, and then we get a list of instruction sequence, and then we split all those sequence in different segments, and meanwhile we calculate the memory commitments of each segment. Hence we can prove all those segments independently. So the very important concept is segments. The segments is a sequence of a MIPS trace with an entry program counter and the image ID. Okay, the image ID actually it's a Merkle root. It's like a Merkle root of the memory space. So each each leaf of the tree is the address value. It's an address and the memory value on that address. So it's more like this architectures. We have a memory page. Yeah, basically the leaf is the page, not the single address, single value on that address. Okay, so we each page is about 4 kilobytes, and the total memory space is 4 gigabytes. Okay, so note that we can handle the memory space up to 4 gigabytes. It's quite different from the RISC-0. So this is also very important difference between the RISC-V and RISC-0 and MIPS. So because we can handle a more larger memory space. Okay. And for the image ID, actually, it's it's more like a memory root, a Merkle root of the memory Merkle tree. Okay, so so basically that why we need the image ID, because when approval gets segments, first it's the approval need to simulate the MIPS VM, so it's need to load the memory and then check the consistency of the memory and the segments of the segments, and then it's will run the segment, perform the instruction in segments, and then get a final states of the memory space. Okay, so again, the VM need to compare the post image ID in the segments and the image ID from the memory space we have in the virtual machine. Okay, so we need to compare the image ID between, that means we have we have one in the segments and we have another one in the virtual machine's memory. So we need to compare if, okay, so those two kind of so all the step transition is correct or are correct. Okay, so that's the first important process of the continuation. Okay, so the second one is we actually we need to aggregate all the proof of each segment. So for example, we have a bunch of segments, and each segment, as I mentioned, we have 6 tables. Basically, we have more than six tables. We have we have 6 because we also need to commit the lookup table, and then for all the tables we use the proof aggregation to get of a single proof. That's a root proof. Okay, so when we have a root proof, we also we need to aggregate all those root proof. Okay, so for this proving process, actually we commit the aggregation computation, and then we use the 2 to 1 aggregation. We get a final aggregation proof, and of course you can see that for this proof, the public input consists of the first block's pre-states and the last segment is post states. Okay, the states would be the image ID and the user's public input. And then we use the group 16 to generate the snag proof of the stacks verifier of the stacks verifier. Okay, so that's another proof recursion. Okay, finally, we have, of course, we can because the segments we can split or program. The program can be can be a simple SHA-2 or it can be a Rust EVM. So for single blocks, take the Rust EVM for example, we have different blocks. When we run the different blocks by the EVM, we generate a lot of segments for a single blocks, and then we first aggregate all the segments for single blocks, and then we also need to aggregate the multi aggregation proof of the multiple blocks. That means we are not just aggregate the proof for each for the different segments in one blocks. We also aggregate all the segments for multiple consecutive blocks. So that's can save a lot of verification fee on layer one. Okay. Yeah, basically that's we produce all the produce all the proof are generated on our proof network. The proof network is also enable use the GPU acceleration to to speed up the proving process. Okay, so the next step I will give an introduction about the dev tool chain. The first is our playground. Yeah, we for our playground here actually it's very it's more like a remix. That means we for developers you can just okay, let me check to the site here. You can paste your okay, it's very simple. It's more like a toy. It's more like a toy. It can help the people that's have even have no knowledge about zk proof. They can try it here. Okay. So you can paste your code here. Like here we it's a SHA-2 sample. So you paste all your code here, and then you use the run to generate the outputs. Okay, when we run it, when we click the run button, actually we send those we send the program to the proof network. Okay, we run the code in the proof network, and then we get the output. Then we can generate the proof. Okay, we have the input and output. When we execute it with the executor, we get outputs. Then we can generate the proof. So it's probably take a while to generate the proof. So the final proof will be listed here. Okay, it's very fast because for the proof network, it just take about seconds, about 10 seconds to generate a proof for the SHA-2. Okay, it's best it's less than 10 seconds, basically. So I think it's very easy for the people to take a first try about the zkVM. And the another part is the zk project templates. Okay, it's more like basically it's more like a developer framework. For example, we have the cargo and the Rust app. Okay, so the zkM project templates is more like a cargo for the Rust. Okay, so we can use the we can clone templates, and then we change we have the Rust SDK and Golang runtime SDK there. The developer just need to focus on the programs. Okay, you just need to take care of the programs. And then we also have we have two different concepts here. The first, the guest and the host. The guest means that's the program that we need to prove, and the host program is and the host part is the program that we interact with the prover and all the proof network, and also we have a verified deploy there. Okay, so maybe we can take a look at the projects, the zkVM projects here. Yeah, basically it's we have such a layout. We have the contracts, we have the guest program and host program. So in the guest program, the developers need to implement the circuits by the Rust or Golang, and in the host program, we have the SDK to or the local prover. Local prover means that we can prove your program on your computer. For the remote proof or networking proof, we can use the SDK to interact with the proof network. Okay, so we also have the tools to fast install to fast install your the environments or the compiler targets the MIPS targets on your in your community. Okay. Also, we have a contracts, and for the contracts we cause we our approver can generate a solid proof with file. So when we generate the with file, it will be used in your contracts. That means when you can use the foundry or use the hard hat. Basically, we are use the foundry here. So when we generate a will file, you can move the will file into this into here, and then you can also implement your other smart contracts, and then imports includes this will file in your smart contracts. So basically, we want to the experienced developers can use the projects templates to build their production-ready zk application. Okay, so another one is the proof network. So the proof network because is kind of a cloud-based proof generation infrastructure. And it's since we can support the continuation, that means we can proving no matter how large your program is, we can prove that we can split that into a bunch of segments and prove them in parallel. Okay, so if you guys are interested in the user proof network, of course you can use the templates, and then but you need to apply, or you need to add your address into our whitelist. It's not permission. It's not permissionless. Okay, so the last part is we need to discuss about the how to evaluate zkVM. Basically, the efficiency is the first point we need to discuss. So basically, for zkMIPS, I think for some cases we are outperformed risk zero. Yeah, there's no doubt that risk zero is the is leading the zkVM industry. Yeah, so there's no doubt that I think, but that's not means for all kind of for all kind of scenario or use case, risk zero is the best. For example, for for the simple computation, for some computation like the SAT3, and we also have another benchmark from from another I don't remember the team of the projects. They also run a benchmark of almost all the zkVMs, and the result is that zkMIPS proof time is the shortest. That means zkMIPS is very solid in the proof time. Okay, so basically, I think zkMIPS, yeah, of course, we release the beta, and in the near future, we will release the production version. I think it will be more ready. It will be more developed. Okay, so we also have some ongoing optimizations. it's really interesting part, I think. Like why we, for example, why we become slow when we perform the SHA-2 chain. Okay, where we have a big proof size in the stack. Basically, that's because we use a different field. Basically, we are all of us are use almost like the risk of zero SP1 or zkMIPS. All of us are using the stack for the virtual machine. Okay, so why we have a big proof size? Because we basically use a different we use a Goldilocks logs. This is the first very important factors that affects the proving process. And another part is because we are use the stacks, so the worker commitments is the take most of the times to at the proving phase. Okay, so how to use efficient hash function? That's become very important. Okay, we have different hash function actually, like the Poseidon, like the Poseidon 2 introduced by the zkSync team. Okay, so basically the different hash function also make difference for the proving. And of course for the field, apart from the from the univariate polynomials, okay, apart from the Goldilocks or M31 or the Big Bear, we also have some new field like the binary. Okay, it's like the binary. Okay, so that's basically that's that's why we have a difference when we use this when we use the stack. Okay, so another part is how to implement upgradable pre-compare. Basically, you can consider all the tables in our all sub table in our zkMIPS is pre-compared. Is a some of them, like the logic, is a pre-compared stack table. So that means when we use the pre-compared techniques, we basically we actually have generates the stack tables offline. So when we run when we simulate the instruction, the instructions, we don't have to generate the stack table in one time. So that would be very efficient to reduce the proving time. Okay, so some other parts is when we also trying to integrate the BWM2 with the zkMIPS verifier. So make sure that we can build a real Bitcoin layer 2. And for the proof side, because we need to it's a single node. It's not a single node. It's need to be trusted by the developers or the users that want to generate proof. If they don't run it on their local machine, they use the proof network, but they need to trust the proof network, right? So that's maybe that's maybe not too decentralized. So that's why we so sometimes we need the trust environment execution technology to make sure that the proof cannot generates or invalid proof. Okay, so like the zkSync and Scroll, they all use the ZTE right now to run the proof. Okay, so basically that's all I want to introduce today. And Yeah. Finally, I need to, I think we have some projects that you can enjoy a try. Take a try. Like, okay, sorry. Okay, sorry. Okay. Okay. Maybe that's all. Maybe if you guys want to take a try of the zkMIPS, just you just just go to read the hub here. Okay, sorry, that's okay. Yeah. So what I want to say is we have the zkM, we have the zkProver, we also have the templates, we also have a benchmark. So you can use the benchmark to to try to compare the zkMIPS with other different zkVM projects. Yeah, like the joints, like the SP1, like the risk zero. So yeah, if you're really interested in the zkVM, it's good to try. Okay, I think that's all for today. Maybe yeah. Do you guys have any questions? Okay. Okay. Okay, let me um go through a simple example. Um yeah. So basically let me uh for example, if I'm a developer, I clone the zk projects templates, and then I have first I have to I will okay. For the first step is I need to install the MIPS registers. Okay. Um, Basically, I have installed the tools. I don't have to install it again because the network seems not stable. So when we install the MIPS toolchain, I I can I can check it if it's already uh there. Okay. Basically, it's the target is already configured here. Okay. So then I can go to implement my programs. So the first step is we may change the let's build on a go now sample. Okay, so let's go to the first example first. And for the first example, actually uh, if we want to build proof or go now programs, we need to make sure understand that uh, we need to prepare some environments like the program name. Okay, the program name and the workspace. So the first is we need to provide a, a, a input here. Okay, this is very important when we want to provide some private inputs here. We need to provide convert it to a byte string, and then use the bin code to encode the your input and assign it and then assign it to the private input string. Okay, so when we have the input, basically we are handle it in the guest program. Okay, so then when we prepare the arguments for the guest programs, and then we go to launch the prover. So we have two options: the networking prover or the local prover. the local approval here. Okay, so that's basically we don't have to modify the host program too much. We just need to change the environments variables and the inputs. Okay, then let's go to the guest programs. Okay, we have basically we have to sample here the add goal, and there are the ROS EVME. So let's go for the add goal here. We actually we have the same structures that to read the reader output. The reader is the input from the host program. So as I said, we have the private inputs and the public inputs. The public inputs should be the first arguments of all the inputs, and the left input would become the private inputs. And then we implement our circuit or circuit here. So the sample here is just perform a very simple calculation. Okay, we add the input and put the input to and change the input. Then finally we can commit the outputs. That means we just return the outputs to the host program. Okay. Okay, so basically that's we need to take care of. We need to note that we need to hand the input and output of a program of your guest program, and then we basically need to go to we need to generate the proof. If we have all the proofs, we have the host program and the guest program. We need to generate proof. Okay, we also have some we also have some scripts here that you can reuse for your program. Basically, it's very simple. We just set up the environment variables, and then we say we use a local approver, and then okay, this is the EF path. That means the programs or the MIPS boundary is generated in the guest MIPS EF at go. It will be here if we compare the guest program. Okay, so then we begin to, and the output is here. That means we will have different segments here, and okay, I can just share because I have run it before. So we can take a look at the segment. Oh, sorry, I have lost. It was deleted. Okay, so basically we can run it here. Okay, so I think it's oh, sorry. I need to here because we need to we need to add the library into the okay, let me use another basically we have the segments here. Okay, so that's the segments. If we have a big program, we maybe have multi segments here. Okay, I think it's very simple to use and because the time is really closing, so we are not run the program. If you guys have any questions when you run those kind of samples, please contact me. So okay, so yeah, so that's basically the questions. And another thing I need to say is we will publish a lot of videos recently to display how to use the template projects and other projects and our zkVM and our project templates. So I think it would be interesting to use if you guys yeah, can take a look at that. Okay, so probably that's all. Okay, thank you. Okay, so I'm not sure which Discord. Maybe you can, yeah, we have a Discord for the zkM. So if you can, you know, if you are in the zkM's Discord, yeah, you can ask a question there directly. If not, maybe you need to add me, or you need to submit. You need to add me to in your Discord or submit. Yeah. Okay. Thank you. Okay. So all issues are welcome. Thank you, guys. So maybe
All right, thank you very much, Stephen. We'll get you added to the zkMonk Discord. If anybody else has any questions, feel free to reach out. Otherwise, thanks everybody for joining today. We can go ahead and wrap it up.
okay. Thank you. Bye.